Okay, so let's start. Okay, so who is Ronak?
Yes, sir.
Yeah, okay. So only you are here, huh?
Yes, sir.
Okay, let's wait for some minute,
Okay, sir.
and then yeah, we will start after 2 minutes. Okay.
Yes, sir. Yes.
Okay. Can you introduce yourself? Where are you from?
I'm from Jharkhand. Currently pursuing my BTech in IT Indore,
IIT
Mechanical
Indore.
Engineering.
BTech.
Yes, sir.
Okay, fine. Hmm. Okay, we will start after 2 minutes. Okay.
Yes, sir.
Hmm. Is my screen visible? Can you tell me, Ronak?
Yes, sir.
Yeah. Okay, fine. Okay, so let's start.
Yes, sir.
Yeah. So, good afternoon, everyone. My name is Rahul Kumar. I'm a PhD scholar in IIT Madras, and this year I'll be a TA for this course, and the course instructor you can see is Professor Atanu Banerjee and Arup Nandi. And usually I will take this live monitoring session on every Sunday from 5 to 7 p.m. And actually, in the last week, actually, I missed this session because I had some problem. I was traveling at that time. Okay, so I will try to cover that week. Okay, so yeah,
Okay.
let's start. Okay,
Yes, sir.
yeah. Okay, so as you already might have seen that in this week, professor has taught the variational calculus. Okay, and he has
Yes, sir.
also introduced some weak formulation of some
Mm.
elasticity problem. Okay, so
Yes. Yes.
let's do some quickly review of the variational calculus. Okay.
Mm.
Okay, so before that, I want to know, can you tell me if more than one member are present, then can you tell me what is functional?
Sir, functional is basically the function of the function. You can say uh, it's function of the dependent variables.
Yeah, those which are functions of functions. Okay.
Yes.
Yeah,
Yes, sir.
good. Okay. Okay, for example, let's take this is a kind of functional. Okay, here you can see that x is independent variable. Okay, independent variable, and y dash are dependent variable.
Dependent.
Okay, so you can see that this I is a function of functions, so that's why
Yes.
here I is called what, functional. Okay.
Function.
Yeah, so let's see some example of functionals. Okay, where we usually encounter some real problem. Okay, for example, one of them is Parkistrochrone. Parkistrochrone. Parkistrochrone problem. Okay, do you know what is this?
Yes, sir. This is the a function in which we find the uh, from which path it will take. If you drop the ball, from which path it will take the minimum time.
Yes.
For that, this
Yeah,
problem
yeah,
is
yeah,
used.
it's correct. So actually, in this, we need to know what will be the optimum path. What will be the optimum path?
Optimum path.
Okay, we don't know what is the optimum path. That we have to determine, such that
Yes.
if block, suppose a block is dropped
Mm.
on this surface which is frictionless, which
Yes.
is frictionless,
Listen.
okay, such that it will take minimum time to reach from this point to this point, and we will measure this y is downward direction. Okay, so
Mm.
from the kinematic we already know that the time taken, I will represent this is also as a functional. Time taken will be from point A to B
E.
is given as ds divided by v.
V.
Okay, and what is v here? V is the
Under root.
velocity. Okay,
Yes.
velocity, not velocity here, we will call it speed, because velocity is a vector quantity. Okay, and here you can
Okay.
see that I am representing v as a denominator, and vector cannot be represented in the denominator. Okay,
Yes, sir.
so here v is called speed of
Mm.
particle,
Okay.
speed of the particle at time t. Okay,
Mm.
so yeah, so this is the problem. Okay, this is called I is called here, I is what?
Functional.
Functional, and we have to minimize. Okay, the solution will be we have to minimize I.
I.
Okay, to get t min. Okay,
Yes.
yeah, so how we will do it? This is one of the problem, and
Mm.
here I will try to write the expression, whole expression. Okay, so
Yes.
A point to B point, and you already know that ds here, if you take a small element here, if you take a
Mm.
small element here, if it is a ds, then
Dx dy.
yeah, dx and dy, then
D.
I can represent ds as a square root of
Dx
dx
square. Dx
square
square dy
plus
square.
dy square. Okay, yeah, so what we have to do is we have to do this thing, dx
Dx
square
square.
plus dy
Dy
square divided by v, and if you take a common as a dx, then it will become,
Yes, sir.
this will become dy by dx raised to the
Yes.
power 2. So I can write y dash
Y dash
square
2.
divided by v, and now the variable becomes dx. So I can write xa and xb. So this is the functional in this case, in this particular problem. Okay, this is one of the famous problem from the variational calculus. Okay,
Mm.
and
Yes,
what
sir.
we will do for v? For v, we will generally, we usually apply energy conservation. Okay, and we already know that from the energy conservation, if the mass of the particle is m, then I can write m v1 square
Dx
divided by 2 plus
square
mg y1. Y1 is what?
equal.
If we consider this as a origin, then suppose I mean, I'm considering somewhere else. So I can consider this distance. If you release from this point, then this point can be considered as a YA. So I can write Y1 equal to mv square divided by 2 plus mgy. Here you can see what? Y is a general and v is the general
General.
velocity at a particular time t. Okay. Then directly we will
Yes, sir.
substitute here. Okay, then
Mm.
we will get the expression of I equal to xa xb and square root of 1 plus y dash raised to the power 2 divided by v1 square minus 2g y minus y1 raised to the power 1 by 2 and dx. It looks little bit complicated from the problem. If you compare from the problem from the professor, then it looks
Yes.
little complicated, but it's not complicated. If you release at the same point, okay, with the zero
Hmm.
velocity, then automatically this part v1 will become
Will be
0,
zero.
and y1 will become 0, and this y will
Zero.
become minus y, okay,
Hmm.
because we are considering, because particle is going in downward direction.
Downward.
Yeah, so that's why it will become minus y, then it will be simplified into the same expression as professor has discussed in the last week, okay.
Yes, sir.
Yeah, this is one problem, okay, from the variational calculus. And there is one another problem that is called geodesic. Have you heard about it?
No, sir.
Yeah, I will tell you. Geodesic. Okay. In geodesic problem, this is also from the variational calculus. It says determine determine the curve determine the curve on a given surface g is a function, okay, g x y z, I mean not a function, this is a 3D graph, okay, or you can say 3D surface, given surface this having the shortest length between two points 1 and 2 on this surface, okay.
Yes, sir.
Are you getting what I'm trying to say?
Yes, sir.
This problem says, suppose you have a 3D surface, okay, some kind of 3D surface,
Hmm.
okay, and there is a point A and there is another point B, and it is saying that can you determine the curve such that the distance between A and B will be minimum, okay.
Okay.
Yeah, this is called geodesic problem, okay. Can you tell me what kind of graph will be that? Just in by your intuitions, tell me.
Linear.
Straight line. You are saying it should be a straight line.
Straight, sir.
Why
Straight line.
it can be? Why it should be a straight line? Because suppose this is a curve, then the straight line is not a possibility.
Yes, sir.
Can you draw a straight line on the surface of Earth?
No, sir.
No. Approximately you can draw. I mean, on the surface of Earth, because we are very small kind of particle on the surface of Earth. So
But
when
that's not
yeah,
really.
but that is not a true. Okay, on
Yes.
the bigger length scale, that is not a straight line. Okay, that is actually a curve. Okay,
Yeah.
so in this problem, you cannot say that the shortest path will be a straight line joining between point A and point B. Okay,
If
so
both points are very close, say that we cannot say that.
yeah, but that is very limiting case. In general, we
Okay.
cannot say.
Okay.
Okay, any kind of curve, when you fragmented in a very small length, that will be a straight line, that is true, but that is a very limiting case, no.
Yes, sir.
In general we cannot say, okay.
Hmm.
So this is
Yes.
also a kind of variational calculus problem, okay. So
Okay.
what kind of functional will be this in this case? So I can write I equal to, suppose a point A and point B, then obviously we will integrate from A to point B, okay, and the distance between A and B will be definitely dx square plus
Device.
dy square plus dz square,
Square.
okay.
Yes.
This is also a kind of variational calculus problem, okay. So simply I can write what, if we take dx as a common, then the variable will become x, so I can write
Yes, sir.
xa
Say 2x.
xb, and this will become 1 plus y dash
dash
square
square
plus z
Z
dash square and dx,
dx.
okay. Again we have to minimize what, I, okay.
I.
The problem is what, we have to minimize I,
I.
okay. And also there is a one more constraint. The constraint is this, Constraint is this.
This.
This is not
What
a
is this?
just, this is not a just this a problem, but there is also a constraint such that when you put x, y, z in the given surface, that should be equal to 0.
Zero.
Okay, so this
Okay.
is a kind of constraint optimization. Okay,
Okay.
yeah, this is
Ah.
kind of constraint such that, I mean, we can write with the constraint, g x y z equal to 0. So this
Zero.
is a problem of constraint optimization. This is a problem of constraint optimization.
So, sir, this thing will be work for all the surface or some a specific surface
For
only?
any general surface, for any general
Okay.
surface.
Okay.
Okay, for any general
Yes.
surface this will be valid. Okay,
Hmm. Yes,
yeah.
sir.
So yeah, I'm not solving any problem right now. I will solve
Ah,
it.
yeah.
I'm not solving problem right now. I'm just introducing everything. Okay,
Okay, sir.
yeah,
Okay, sir.
then we will solve it. Okay, and there is a one more problem which is also very famous and you will see in the finite element. Okay, this is called isoparametric problem. Okay, in this problem, this is also a constraint optimization problem. Okay, so it is saying that find find the family of curves which are closed which are closed close to each other. Okay, such that
Yes, sir.
the area formed by them will be maximum, and okay,
Yes.
such that there is one more condition, such that the total length length formed by them will be L. Are you getting my point? It is
So,
saying
sir,
that
if this total length is parameter thing,
what?
this total length is perimeter.
Yes.
Okay.
What it is saying is find the family of curves such that when they close to each other, then they will form a surface, or you can say area, and that area should be maximum.
Maximum.
Okay,
Yes.
and the parameter should be a constant length.
Hmm.
Okay, like consider you are taking a string. Okay, you are
Okay.
taking a
Ah.
string of constant length L. Okay,
Hmm.
so can you find a curve such that when you close the string, then the area will be maximum?
Okay.
That is called what? Isoparametric problem.
Okay.
Okay, so what?
Yes.
So here, what is the functional? The functional is we have to maximize the area. We have to maximize the area.
It-
This is the expression of area. Okay, such that,
Yes.
okay, such that
Hmm.
here what is the constraint? Constraint is L. We already know L. Okay,
Okay. This.
or you can write, I'm introducing another parameter, or another, you can say, independent variable. So I can write what? Dx by d tau raised to the power 2, and dy by d tau
This.
raised to the power 2, and d tau.
Double.
Okay, here also I can write what? If I introduce tau, then I can
Tau.
write
X divided
x
theta.
dy by d tau
Theta.
minus y dx by d tau
Theta.
and d tau.
Theta.
Can you tell me, can you derive how we will how we are getting this expression of area? Expression of area
Uh,
by enclosing by any surface or in any curve.
I'm not
Okay, fine.
remembering it, sir.
Yeah.
But I have shown this thing.
Okay.
Actually, derivation part.
Yeah, it's fine. It's fine. Let's derive this. Okay. You
Okay.
already
Yes, sir.
know for 2D, for two-dimensional curve, we already know that that will be given by double integral of dx
X and
dy.
dy.
Okay, we already know that dx dy. Now it is saying that the area will be this. Okay, the area will be this. So I will apply the Green's theorem. Okay, from Green's theorem. Do you know that from Green's theorem?
No, sir. I know.
Okay, Green's theorem. Green's theorem says, suppose you have a enclosed curve m dx and n dy, then it will be converted into a double integral. And this is a enclosed curve. Okay, it will be converted in the double integral, and I can write partial
Del M
derivative
by
of
del.
del n by del y minus partial derivative of m del x, and here I can write dx dy. Okay, so now you can see that del x del n by del y, del here n is what? N is minus 1, so you can see that will become minus 1, and del m by del x again that will be 1, so
1.
that will become 2 times, and when you cancel out with 2, then it will become this area. Okay,
Okay.
so these two,
Yes, sir.
this expression and this expression both are same,
Sure.
but has been fragmented into a what? This is kind of which integral? This is line integral.
Line.
Okay,
Tan into. Yes,
this
sir.
this
Yes,
is
sir.
a line integral, closed line
Yes, sir.
integral.
Yes.
Okay, closed line integral. Okay, so this is also a kind of constraint optimization where we have to maximize this area by using the constraint this. Okay,
Mm.
so yeah, so these three are very famous problem for the optimization. Okay, we will solve it. Okay, so quickly, I will review that variational calculus with a delta operator. Okay, then we will try to find the Euler-Lagrange equation, and then we will try to solve these three problems. Okay, so
Okay, sir.
yeah, let's move the delta operator. Delta operator. In this class, I will not solve the assignment problem because there is a due date. Okay, there is a due date on 8th August.
Later.
Okay,
Yes.
so because of that, I will not solve in this week. In the next week, I will try to solve. Okay, because
Sir, I have problem with the assignment problem. You just
second.
tell me what.
Okay, fine. But you know there is a problem. If I solve it, then there is no meaning of the assignment.
No, sir. I'm not saying you solve. That's just a conceptual. There is some cost.
Okay.
I can how can I say. There is
Okay.
a thing which I don't
Okay,
exactly
maybe
remember.
maybe when I finish this
Ah,
session, then you would be. I think you would be able to solve that problem also.
okay, sir. It's
Okay.
not like that, sir. There is problem in the question.
Okay.
According to me,
Okay.
just
Fine.
you confirm that thing. Is there error in the question, or that is not
No,
the
that
question
that
is
problem is actually very standard. Though whatever they have uploaded on the portal, those are very
okay?
standard problem and they are very old. Okay,
Okay.
so it's not like every year there might be some changes, but not all.
Hmm.
Okay, so those are very standard problem. Okay, so
It's basically like, sir, if I can tell you the
hmm.
for Rayleigh Ritz method, we
Okay,
need to get the variational method as a bilinear.
okay,
The in variational method, the part of which we say AUE
hmm.
matrix, that
Hmm.
should be bilinear. But the problem which I've given,
Hmm.
there is the variational statement is not in the form of bilinear, and from that thing we cannot can go to the Rayleigh method.
Okay.
But they said to from that variational statement we have to derive the Rayleigh method a
Okay.
statement.
Okay. We will see at the end
Okay.
of the class. Okay.
Yes, sir.
Yeah. Okay. Yeah. Okay. So yeah. So let's see what is the delta operator. So in the delta operator, the same thing we do. So suppose we have 2 point xa xb, and this is the standard solution. This is the exact solution. Okay,
Okay.
that is called y. Okay, and we have to find, we don't know what is y, we don't know what is y. So
Why?
what we do is we vary we vary y we vary y from small changes,
Hmm.
and that is called
Delta.
y tilde, and that
Okay,
is
sir.
y plus epsilon
Delta.
eta. Okay, and there is a condition is that eta a eta a equal to eta b, that will become 0, which means that at the end point this variation should be
Should be
0. So
zero.
actually the
Hmm.
variation of y, that is nothing but the difference of y tilde minus y. So
Why?
you can think about like this. Okay, so this is, suppose that you are considering this as a y tilde. Okay, so the distance, the vertical difference is what? Delta
Delta.
y. Okay,
Why?
this is called variation. Okay, so because of this we get insight. Because of this we get insight. Suppose we have the functional f. Okay, and if we change, and this functional is suppose a function of x, y and y dash, and like that. Okay,
Hmm.
and if we change this functional by an increment like this, y plus epsilon
Delta
eta
Y.
y dash plus epsilon eta dash. Okay,
Hmm.
then we get an insight. And if we change this, then from the Taylor series expansion we know that I can write f x. Now I can write here as a y tilde, and this one I will write y tilde dash. So I can write
Okay.
y tilde y tilde dash. Then I can write
Hmm.
y from Taylor expansion, x y y dash plus del f by
Delta.
del y del y plus
Hmm.
del f by del y dash plus higher order terms.
Okay.
Okay, for
Hmm.
then now if I move here, this, okay, this will become f tilde. Okay, this is because you are changing the y to y tilde and tilde dash, then it will become f tilde. So I can write f tilde minus f, and this will become del f here also. Okay, yeah. So del f by del y plus del f by del y dash. Okay, plus,
Yes.
yeah, second order term. Okay,
Hmm.
so this term is called the first variation. First
Variation.
variation. This term is called first variation.
First.
Okay, so which means that from the when you want to maximize the single variable calculus, when you want to maximize the single variable, you already saw that we have to find the extrema, we have to find the del y by del x equal to 0.
Hmm.
Okay, in the same, and this is nothing but the first derivative. In this case
Yes.
this is called the first variation.
Variation.
Okay, so which
Okay.
means that if you want to maximize, if you want to extremize I, then what you have to do is you have to extremize del I. Okay, you have to extremize what? Del I. Okay, and then you have to find what? Del I tilde del y by putting epsilon equal to
Then equal
0.
to 0.
Okay, and here it will be del tilde. Okay, so then this is nothing but the first variation of f, and you have to substitute epsilon equal to 0. Okay, then you will get the optimized optimized function f. Okay, so
Yes,
yeah,
sir.
so this is the problem. So when you put I when you put I here, then you will get Euler Lagrange equation, and that will become del f by del y minus d by dx
Hmm.
del f by del y
Del
dash
Y.
equal to
Del.
0. Okay, after
Okay.
substituting I tilde here, then you get this, and this is called what? Euler Lagrange
Elements.
Euler
Yes.
Lagrange equation. Okay, so the whole problem where we will solve will revolve around this expression, but this is not a just expression. This is very simplified expression where the functional is just a function of y and y dash. Sometimes
Okay.
there will be several independent variables, sometimes there will be several
Hmm.
dependent variable. So
Hmm.
accordingly this expression will change. Okay, but
Okay.
for this moment we will stick with this Euler Lagrange equation. Okay, fine.
Fine, sir.
Yeah, so let's solve very simple problem. Okay,
Hmm.
find the curve
Yes, sir.
find the curve y equal to yx yx of minimum length minimum
Then.
minimum length joining joining two given points a aya, and second point is b byb. Okay, here in the xy plane, can you tell me what will be the solution in this case intuitively?
Only in XY, matlab, this surface is XY plane
Hmm.
here. Then the and the curve of minimum length. The line joining these 2 points,
Yes, in
linear
this case the solution will be a straight line joining these two
these
points.
points.
Okay, this is also a geodesic problem, but with the very simplified version. It is a
Also,
very simplified version of geodesic problem.
basic,
Yeah, so it is also a geodesic problem. Simplest, I can say,
simplest
simplest
geodesic.
geodesic. Okay, so let's solve this. Okay, so what will be the functional? That will be integral of a to b,
It will be
and in this case 1 plus y dash square
square
dx.
d.
Fine.
Hmm.
What will be the distance between, I mean, if you take this small element, and that element will be what? ds, and that ds will be simply dx
dx square
square plus dy
plus
square,
dy
and if you
square.
take dx as a common, then it will become
Yes.
this.
Yes.
So what we have to do? We have to minimize I. Okay,
This.
what is the problem? To minimize
Mas-
to minimize I. Okay, and here what is f? F is simply 1 plus
Under root
y
y
dash
dash
square.
square.
Okay, so let's solve this. What we will do? Simply del f by del y
Del y.
minus d by dx and del f by del y dash
Del
equal to 0.
equal
So here you can see that there is no such expression for y, so
y
simply it will become 0.
0
So d by dx,
d.
but now there is an expression of y dash, so we
Yes.
have to find the partial derivative of this, so that will become 1 by 2 square root of 1 plus y dash
Y
square into 2 y
Y
dash
dash.
equal to 0.
0.
Okay, so I will integrate directly. I will not differentiate here. I will directly integrate, and if you integrate, it will become
Ah,
y dash divided by square root of 1 plus y dash square equal to c. Can you see there?
okay.
I can directly move here and it will become integral. And if you
Ah,
integrate it, it will become this.
yes, sir.
Okay. Now,
Hmm.
now I will square both sides. So this will become y dash square
That is
equal to c square 1 plus y dash square.
wider.
And if we take common of y dash square, it will become 1 minus
One of
c
C
square
square.
equal to c square, and y dash equal to c divided by 1 minus
One
c square.
C.
Now I can write y dash as a dy by dx. So it will become dy c dx divided by 1 minus c square. Now I
So
can,
there will be plus minus, not the plus minus thing.
you can take it.
Okay.
You can take it, but you will get the
Okay.
same result.
Okay.
Okay, there will be a family of curve here, but
Hmm.
when you put the boundary condition, you will get the same result.
Okay, sir.
Okay, so what will be here? So y equal to c divided by 1 minus c square x plus d. Here you can see that this is nothing but a constant.
Hmm.
Here I can
Okay.
take as another
Okay.
constant kx plus d. So here you can see that the solution will be a straight line. Okay, now simply if it has given the boundary condition, then the solution will be what? Y equal to yb minus ya divided by b minus a x. Okay, plus here will be what? Ya.
Hmm.
When you take the boundary condition, you will get this solution.
Yes.
Okay, so yeah,
There
this is
should be
also,
x minus x in x
hmm?
minus a.
Yeah, here
X minus
x,
x.
yeah, x minus xa. Now it's fine.
Only. Yes, sir.
Yeah, so here it will be a solution. Okay, now let's move to the another geodesic problem. Okay, and that will be a very little bit lengthy, and that is a problem of like sphere. Suppose consider a sphere.
Okay.
Consider a sphere of radius r. Radius r having its center
Same.
at the origin.
Origin.
Okay,
Yes,
origin,
sir.
and we wish, and or you can say we want to determine the shortest, whatever I introduced the second problem, the shortest
Okay.
path
Hmm.
between two points,
Points.
okay,
Hmm.
on the sphere. Okay, so yeah, so this is the problem. In the 3D I can represent this as like this. Okay, and there are 2 points,
Hmm.
A and B.
B.
Okay, now I want to find a path between A and B such that the distance between A and B will be minimum.
Hmm.
Can you tell me what will be the answer intuitively?
Uh, Not facing, sir. It will be
You can consider our
quadratic.
earth as a surface. You can consider our
Quadratic.
earth as a sphere.
One second.
You can clearly see that the distance between A and B on the surface of earth, are you listening to me?
Yes, sir.
Yeah, so there is this distance between A and B will be the curve, not like zigzag path. The path should be a straight line, but exactly on the surface of earth. Okay,
Okay.
like uh, like the curve on the you saw that the map of the earth, right?
Yes, sir.
So all the longitudinal, latitude, all are like this, right?
Yes, sir.
This, this, this. Okay, and
Mm.
in the horizontal direction it is something like this,
This.
right?
Yes, sir.
So what are these? What are these? These curves are actually a circle.
Yes, sir.
These curves are actually a circle
Circle.
which are
Yes.
surrounded on the earth surface.
Mm.
Okay, and any 2 point, if you take any 2 point on this circle, then
Mm.
that distance will be the shortest,
Yes.
and that is called what? The great circle. The great circle.
Okay.
Okay, those circles are called what? The great circle.
Yes, sir.
Okay, so how we will solve it? To solve this, I can consider point in the polar coordinate, not polar, spherical coordinates. Suppose
Okay.
if the radius of the earth is r, or a sphere, so I can write in the polar coordinate r sine theta cos phi, and y equal to r sine theta sine phi, and z equal to r cos theta. Okay, so what will be the distance between these 2 points? The distance between ds square equal to dx square plus dy square plus dz square. Okay, so the functional will become p to q, or here in this case a and b.
Okay.
A and b,
B.
and that will be dx square, dy square, and dz square. Okay,
Yes.
so here I have to substitute dx, dy, and dz using these three equations. Okay, so when you differentiate x, y, and z like this, dx, dy, and dz, by considering theta and phi as a variable, then you know what you will get when you simplify it. So dx square, dy square, and dz square, when you substitute, I mean when you differentiate it, so here I will not differentiate completely. I can write like r cos theta cos phi d theta plus r sin theta, and here minus sin phi d phi. Okay, similarly you have to do for dy and dz, and when you put everything here, then dx square, dy square, dz square, it will become d theta square plus sin square theta d phi square. Okay, when you simplify it everything, then it will become something like this. Okay, now I can directly substitute.
Sir, R should be there now.
Yeah,
Maybe
r, yes, r will be
R
also
is
here.
part.
Yeah, r will be also here, and when you substitute everything here, then r will be common, because there will be square root also, and it will become d theta square plus sin square theta and d phi by d theta raised to the power 2, and I will take d theta, and here will be d theta a to d theta, sorry, theta a to theta b.
B.
Okay, so this is the functional where we have to optimize, but it is in the polar coordinate.
Yes, sir.
Okay, so what directly I will apply Euler-Lagrange
Sir, d
equation.
theta will be there or 1 will be there?
Yeah,
D
there will be
theta.
1 here, it will be 1, sorry, it will become 1, yeah, sorry, yeah. So I will apply Euler-Lagrange equation, and that is what? Del f by del y minus df by dx. Okay, and del f by del y dash equal to 0. Here in this case y is what? Phi.
Phi.
Okay, and x is what? theta.
theta.
And y dash means phi dash.
Phi dash.
Okay, and f I can see this is f. Okay, so you can see that there is no such expression of phi. Okay, so this part will become 0
0.
minus dy. Okay, here f will not come. Okay, so and also it will be d, not del. Okay, so this will become d by d theta del f by del phi dash equal to 0, and I can write d by d theta, and when you find the del f by del phi dash, then you will get 2 phi dash sine square theta divided by 2 square root 1 plus sine square theta phi dash square equal to 0. Okay, so
Okay.
again I will directly integrate. I will not differentiate here, because when you differentiate it, then this expression will become lengthy, and again you have to integrate it. So that
Okay.
will be a kind of stupid thing. So directly I will
Yes.
integrate both sides.
Yes.
So and here 2 will be cancelled out, then it will become sine square theta phi dash divided by equal to c1.
C.
Okay, and I will square both sides, then it will become sine raised to the power 4 theta phi dash square, and this will become, okay, I will take this as a constant k, not c1, because later we will use c1.
Okay, sir.
Yeah, so k 1 plus sine square theta and phi dash square, and I will take phi dash square, phi dash square, this will become sine raised to the power 4 minus k sine square theta equal to k square, and now it has simplified like this. Okay.
Okay, sir.
So again this is a differential equation, and when you take a square root, it will become phi equal to integral of k d theta divided by sine theta, and this will become sine square theta minus k square and d theta. Here you have to integrate it, and here for the integration we have to substitute tan theta equal to 1 by eta. Okay, this problem is already solved, but I'm just showing how to solve. When you solve it,
Sir,
then
what
you
is
will get
the 1 by eta?
eta is just a parameter. I'm just substituting this eta, and whatever I told you earlier, that eta is different. I'm just substituting
Okay.
to integrate this,
Okay, sir.
because after substituting this integral will become very easy. Okay, so what it will become 1 plus eta square d eta. Okay, when you substitute everything here, then it will become something like this: 1 plus 1 by eta square 1 by 2 1 plus eta square minus k square. Okay, and when you substitute this, there will be another constant, because this is a derivative, right? So when you integrate it, because it is a definite integral, so I will take another constant here. Are you getting what I'm trying to say? Because you are here, it is a derivative. Okay, so when you integrate
Okay.
it, and since
Yes,
you are
sir,
taking
yeah.
indefinite integral, then another constant will come. Okay,
Yes.
that's why I was taking k as a constant here, and
Sir, we have not integrated yet, na?
I have integrated here, no, because it is a derivative.
Sir, yes, sir. This one is d5 by
Yeah,
d theta.
yeah.
You
This
have
is
only changed
yeah.
the
This
d theta to you taken to the RHS, and this thing is not yet integrated.
yeah, this one is not integrated yet. This one is not integrated yet. This is just a integral constant. which
Okay.
came because integrating of this phi.
Yes,
O-
sir. So if we integrate this field, then we'll right. If we integrate in the left hand side, then we should integrate on the right hand side. No, right hand side is not completed yet. No.
Uh, why there is such confusion? Because when you take a square root, then it will be something like this. Square root will come here, right?
Yes.
And here phi dash. Phi
Yes,
dash
sir.
means what? D phi by d
I
theta.
know. Theta. Yes, sir.
Okay? And
Mm.
just send d theta here.
Yes, sir.
Okay? And now you have to integrate it. So
Yeah.
here d phi will become phi.
Okay.
Okay?
Okay. So
Then
C1
constant
is
comes.
C1 is the due to integrating the dphi.
Yes.
Okay, sir.
Okay?
Okay.
That is the
Okay.
because of the integration of phi.
Phi.
Okay? So here the another constant comes.
Mm.
Okay, so now let's take, because you can see that here there is a repetition of 1 by 1 plus 1 divided by 1 plus eta square. So I can write, or I can write phi equal to, here when you substitute 1 by k square minus 1 raised to the power 1 by 2 as a c2. Okay, when you substitute this, then you will get phi as d eta divided by 1 divided by k square minus 1 minus eta square raised to the power 1 by 2 plus c1. Are you getting what happened here?
C2 where we have to where the C2 go.
Here you can see this will be cancelled out. 1 plus eta square 1 plus eta square whole will be cancelled out. Okay, then another constant I kept it 1 by, I mean when you simplify it, when you simplified all this, then it will become this.
Okay.
Okay,
Okay, sir. Okay,
yeah,
sir.
then I will use this,
Okay.
use this as a c2. Okay,
Mm.
then it will become phi equal to, and it is nothing but the integral of, here it is a variable c2 minus eta square, which means that it is an integral of 1 divided by something like
But
a
minus
square minus x square
X square.
dx. Okay, so
Yes.
it will become, when you substitute here c2, then it will become phi equal to sine inverse c2 eta. Okay,
Eta.
plus c1. This is another constant. Okay, I mean we constant which came earlier. Okay, so this is the solution. Okay, now substitute everything. Phi equal to sine inverse c2 divided by, because eta was tan theta.
Mm.
Okay, plus c1. Now I can write like this: sine
Sine
phi
phi.
minus c1 equal to c2 divided by tan theta. Okay, and when you simplify everything, and also by taking this thing in a spherical coordinate, x equal to r sin theta cos phi, I will write the final expression here. When you simplify it, like it will become sin theta sin phi cos c1 minus sin theta cos phi sin c1 equal to c2 cos
Cos
theta.
theta.
Okay, then you can see
Yes.
that sin theta sin phi sin theta
Sin
cos
theta
phi is
cos
nothing but
phi.
x and y. I mean
Yes.
not x and y, x by r and y by r.
And Y by R.
Okay, so here it is y by r, y by r cos c1 minus x by r sin c1 equal to c2, and here it is z by r. Okay, this then final expression will become y cos c1 minus x sin c1 equal to c2 z. Now you will see what is this. What is this? What is the locus of this equation?
Locus of this is a circle.
Not locus, just tell me what kind of equation is this? It's a straight line, plane, circle, parabola. What is this?
Not sir. Maybe circle is
Circle? How it is circle?
not knowing, sir. Just say
Equation in circle is something like this, no? X minus
x
x
square, sir.
square
Yes, sir.
plus y minus b square equal to c square, like this.
Yes, sir.
Here it is a form of something like ax plus by plus cz equal to d.
A line.
Hmm?
Oh,
Line
line.
z is appearing here. How it should be line? It is a equation of plane,
Plane. Okay, sir.
3D plane.
Okay.
Okay, it is a equation of
Yes, sir.
plane,
Plane.
and this plane is nothing but the plane of great circle.
Okay.
It is a equation of
Plane of
plane of great circle,
great circle.
which means that this plane is nothing but the, when intersect this plane, this plane is nothing but the this plane, and this plane when intersect this sphere, then
Mm.
that circle bit, because it will become a circle, right? When this
Yes,
plane,
sir.
any plane intersect this circle, this sphere, it will form a circle.
Yes, sir.
And the biggest part is this plane is passing through origin. You can see that passing through
Through
origin.
origin.
How you can see that it is passing through origin?
Putting x, putting two coordinates equal to 0, and another
Yes.
coordinate.
How I am clearly saying that when plane which is passing through origin, it will definitely make a circle on the sphere. Suppose such plane which is not passing through the sphere, not passing through the center of the sphere, is
Okay.
there any guarantee that it will form a circle?
Yes, sir. And any plane that would intersect, it will actually form the. My intuition is saying that.
Yeah, that will be a circle, but that will
Yes.
not a great circle.
Okay.
That will not be a great circle.
So great circle is a thing which
The
only pass through
greatest,
the center.
the greatest circle on the surface of Earth or surface of a sphere. The great circle means the surface, the largest radii of this, the largest
Okay.
radii containing the circle.
Okay.
Because
Okay.
when plane which is not passing through the origin will also form a circle, but the radius will be not the largest.
Yes, sir.
The radius is the radius will not be the largest.
Largest.
But when the plane which is definitely passing through the center of the sphere, the radius will be the largest.
Yes,
And
sir.
that circle, that circle will called as the great circle.
Yes, sir.
Okay, and it is sure that when you take any 2 points on the great circle, then the distance between those two points will be minimum.
Okay.
Okay, I will show you with the animation. Wait, I actually wrote a code.
Okay.
I wrote a code on Mathematica. I will tell you. I will show you. It will show the animation. See here this is the same equation. You can see y cos c1
Yes.
minus x
Yeah.
sin. Is it visible?
Yes, sir.
Now it should be visible, right?
Yes, sir.
Yeah. So you can see that I'm plotting 3D plot with the function y cos c1 x c1, okay, divided by c2, and I'm varying x from -1 to 1, y is also -1 to 1, because I'm taking the sphere of unit radii. Then the variation of x will be what? -1 to 1, and y will be also -1 to 1. Okay. So yeah, and this is the equation of plane. This is the equation of plane, and also I have created a sphere with
Yes, sir.
with origin as a center
Origin.
and
Yes.
radii 1.
One.
Okay, now I will show the animation. See, and here you can see that c1 and c2 were the parameters.
Yes, sir.
Because when you vary c1 and c2, it will give a family of planes,
Okay.
not just one plane. Okay, when you vary the value of c1 and c2, because there will be infinite number of great circle on the sphere, right?
Yes, sir.
Okay, so
Yes, sir.
that's why I'm varying C1 and C2, and you will see here it is forming a circle, right? It is a sphere,
Yes, sir.
it is forming a circle. See how it is rotating, not it is showing properly. Yeah, see, see how it is
Yes,
rotating,
sir.
see how
Hmm.
it is rotating, right? See, this circle is
Yes.
rotating, right?
Yes, sir.
See how it is rotating.
Hmm.
Hmm? So
Sir, this is a sphere
every
or
circle is
this
a
is
great
some
circle.
oval shape?
What?
This seems like some oval shape. Is this a sphere or due to the uh,
It is a sphere, but actually this is not visible like a sphere because
yes.
yeah, because of that cropping thing. It is actually a sphere. It some
Okay.
seems like a ellipsoid, but it is a sphere
Yes, sir.
actually.
Okay.
It is a sphere, okay? Because
Okay.
I already showed you, no, radius is one,
Yes, sir.
and because of this
Yes, sir.
diagram is
Yes, sir.
not exactly complete, but it is a sphere, okay, like this.
Maybe the scaling
No, no,
is not
everything is correct. See, z is
okay.
minus 1 to 1,
Hmm.
okay,
No,
y
sir.
is
I am saying about the scaling.
scaling,
A scaling of the z
scaling
axis.
minus 1 to 1, minus 1 to 1, plot range, okay, yeah, everything is fine, no, here you can see plot range minus 1 to 1, minus,
No, sir.
sometimes
I'm not
in
saying about.
Mathematica it doesn't show
Uh,
exact picture,
okay.
but yeah, but it is a sphere for sure.
Okay, sir.
Yeah, okay, so here you can see
Okay.
that it is a great circle, it is a family of planes, okay, when you change
Hmm.
the value of c1 and c2, it will become a family of planes.
So all these planes are passing through the
Center,
center of the.
yes, all these planes are passing through the sea, all these planes are passing through the center of the sphere,
Okay, sir.
okay, and it is forming a sphere.
Okay.
Here you can see it is forming a sphere. Sorry, it's a
Okay.
circle,
Circle. Yes, sir.
okay.
Okay.
So yeah, this is a one geodesic problem, okay.
Hmm. Hmm.
Okay, now let's solve the isoparametric problem. Do you want to see how to solve?
Yes, sir.
Yeah, let's solve the isoparametric problem, where I already solved one thing, no, but that is not constraint, that is not a
Hmm.
constraint basis, okay. So let's
Yes,
solve
sir.
the isoparametric problem. Okay, and this isoparametric problem is the constraint optimization, okay.
Okay.
This is called what? Constraint optimization, where
Hmm.
we have to to extremize. In this case we have to extremize I tilde with x1 x2 with functional f x y tilde dash dx with constraint j tilde equal to x1 x2 g x y tilde dash dx, and this will be a constant.
Hmm.
Okay, here tilde I am representing because I have already varied y as a y plus epsilon eta. Okay, so what we have to do is we have to actually find the derivative of this by taking the constraint of j. Okay, so in this
Hmm.
case when you solve the constraint kind of problem, then what you have to do is you have to take f, you have to take f as a f star,
Okay.
and that will become f star is, that is f plus lambda g, or you can say in this case that is j. Okay, we have to do nothing, we have to do just we have to change f as a f star plus, so
Okay.
f star equal to f plus lambda j, and here lambda,
J or G, sir.
here in this case j we are yeah, okay, okay, sorry.
So we have to consider the integration part. Okay.
Yeah, here
G.
it is g, okay,
Only G.
not j,
Okay.
it is g, and here lambda is called Lagrange multiplier.
Is it? constant or a variable? मतलब this
What?
is
Just
vari-
lambda.
yes sir. Lambda is
Lambda.
varying thing.
What?
Lambda is varying variable thing, or this is the
Yeah,
predefined constant.
this is a variable. Actually,
Okay.
you have to eliminate this lambda.
Okay.
You have to eliminate this lambda. I will not go through the derivation how we have
Okay.
derived this, but for
Okay.
sure, when you take f as a f star, where f star is f plus lambda g, and when you
Mm.
take the derivative and when you apply the Euler-Lagrange equation, then you will get two equations. You will get
Two
two
equation.
equations, and when you eliminate this lambda,
Mm.
then you will get one isolated equation, and that we have to solve. Okay, I will give you one example. Okay, so what will be the Euler-Lagrange equation in this case? In this case, Euler-Lagrange equation will be del f star divided by del y minus
Minus
d by
divided
dx del f star divided by del y
del by
equal to 0. This is
0.
the modified Euler-Lagrange equation when there is a constraint optimization problem. Okay,
Okay. Okay.
let's solve one problem. Okay, like not one, that isoparametric problem. Okay,
Mm.
and what was that? Okay, and that was nothing but I equal to a, that we have to maximize, right? 1
Yes.
by 2 x1 x2
2x
x dy by d tau,
dt.
okay, minus y dx by d tau d tau. Okay, this is I.
Sir,
Yeah, tell me.
sir, limit should be tau 1 to tau 2.
Oh yeah, yeah, tau 1 to tau 2, tau 1 and tau 2. And what is the constraint that we called j, and that is
J.
given? That should be
Mm.
constant length L. Okay, and that will be tau 1 to tau 2
Tau 2.
integral
One.
dx by d
D
tau
tau.
raised to the power 2 plus dy by d tau
D
raised to
tau.
the power 2 d tau. Okay, so here what is f? Here this one is f. Okay,
This one.
not this, I mean this 1 by 2 including 1 by 2.
Okay.
Okay, including this 1 by 2 as
Back to
f. Okay, and this one is g.
G.
Okay, so what is the f star? F star will be f plus
Plus
lambda
lambda G.
g. Okay, now apply that Euler-Lagrange, modified Euler-Lagrange equation. So here f star will become 1 by 2 x y dot minus y x dot plus lambda x dot square plus y dot square raised to the power 1 by
Half.
2. Okay, so here you can see that there are two independent variable.
Yes.
Sorry,
Two
not independent variable. Here there are two dependent variable.
dependent is.
Okay, there are two dependent variable. And what are those?
X and Y.
X and y.
Y.
And there is one independent variable. Okay,
Mm.
there is only one dependent variable, sorry, independent variable.
In.
And what is that? Tau.
Yes.
Okay, so what we will do is, as sir has already derived, when you see two dependent variable, then what we
Yes.
have to do is, we have to
With
make a coupled differential equation. We have to make series of differential equation, right? So in this case what we will write is del f by del x minus d by dt, not tau, It should be
Yes.
t here in this case, not tau, because tau is inside the integral, but what is the independent variable? That is t, right? Or you can
Okay.
also consider there is no difference t and tau, anyhow that is the variable. So what is that? dt
D2.
del
Del F
f star by del x dot
dot
equal to 0. This is one equation. And another is
yes.
what? Del f star
Dot
by del y minus d by dt
D2.
del f star divided by del y dot equal to 0. Can you see that?
Yes, sir.
Yeah. So from the first equation, what we will get? When you find this using this equation, you will get 1 by 2 y dot minus d by dt
D2.
minus y by 2 plus lambda into 2 x dot by 2 square root x dot square plus y dot square equal to 0. And from this equation you will get 1 by 2 minus x dot, right? d
Yes.
by dt x by 2 plus lambda y dot divided by square root of x dot square plus
Y.
y dot square equal to 0.
0.
Okay, this is two equations.
Yes, sir.
Okay,
Hmm.
then what we will do? Tell me.
We will go integrate.
Yeah, so no, here you cannot integrate. Here you cannot integrate. Here you have to eliminate this lambda. Okay, so first simplify it. Okay, this is what.
Sir, can't we integrate y?
Yeah, you
Y
can
dot?
also integrate, because here dt is the independent variable in both sides, right? Because y dot we can also write dy by dt, and x dot
Yes.
we can also write dx by dt.
Dx
So I
by
can
dt.
directly integrate it also.
Okay.
Fine?
Okay, sir.
Are you getting it?
Yes, sir. Yes.
Yeah. So from this equation, you will see y minus lambda x dot divided by x dot square plus y dot square raised to the power 1 by 2 equal to c1. Okay, fine. You can
Okay.
see when you
Yes, sir.
integrate, it will become y, and
Got that.
this will be simply,
Okay.
okay, this will become this.
Yes.
And similarly, when you integrate this one, you will get x plus lambda y dot divided by x dot square plus y dot square 1 by 2 equal to c2. Okay, now you can see there are two equations, and you have to eliminate this lambda.
Left hand.
Okay, and when you try to eliminate this lambda, you will get x minus c2 dx plus y minus c1 dy equal to 0.
Okay.
Can you see that? When you eliminate lambda, you will get this, and this is called, this is what? Differential equation. Okay, and this differential equation is of the form m dx plus
Dx
m dy
and
equal to 0.
0.
Okay, and this, when you solve this equation, you will get a equation of circle.
Okay.
Okay,
Yes,
this
sir.
is the equation of
Circle.
circle. And it's true. It's true. When you take a string of constant length L, suppose when you take a string of constant length L, and someone wants what will be the maximum, I mean what kind of curve such that there is a maximum area,
Hmm.
then you can form a circle only.
Okay, sir.
And what kind of curve when you want to get a minimum area?
Minimum area. I'm not getting.
That is very trivial problem. Okay, if when you want a minimum area, then their area will be minimum,
Sir,
that area will be 0. Simply just make like this.
Okay.
Okay, just make like
Okay.
this overlapping of the, suppose you are taking a string and
Mm.
just overlap like this, the area will be 0. And what kind of
Okay.
curve is that? Any kind of curve you will get that.
Yes, sir.
Any kind of curve you will get that. That's why that is not a optimization problem. That's why here
Okay.
we are getting a maximum area, not minimum area.
Okay.
Sometimes people ask one question like, how you know that this will be a maximum, not minimum?
Mm.
How do you know that this is a problem of maximization, not minimization?
Yes, sir.
Okay, so that thing we cannot say directly, that thing we will
Okay.
say intuitively.
Okay.
Okay, sometimes
Mm.
more than till now only second, I mean two variable calculus problem also only we actually see that the problem is optimization of maximum or minimum, but more than
Mm.
two variable it's very difficult to say.
Okay.
Okay, so
Yes, sir.
intuitively we say that yeah, this is a problem of maximization,
Mm.
because anyhow you cannot solve every differential equation. That's why it's not possible to solve every extremization problem analytically.
Okay.
Are you getting it?
Yes, sir.
Yeah, so yeah, this is a one isoparametric problem. Okay,
Okay.
now sometimes you encounter a problem of boundary condition, because you
Yes, sir.
don't know whether what kind of boundary condition, because after getting the differential equation you still don't
Mm.
know what kind of boundary condition you are taking it.
Mm.
Okay, so suppose you have a functional like this, you have a functional like this. Okay, and you know that if it is
Wait.
given ua equal to ua,
Mm.
ub equal to ub,
Yeah.
okay, and let's take a variation.
Mm.
Let the variation is alpha v. Okay, so what will be the
Okay.
modified u? That will be u tilde, will be u plus alpha v. Okay,
V.
and with the end condition, like we already saw that what will be the end condition? With end condition should be va, right? Va equal
Ah.
to vb equal to
Is equal
0.
to 0.
Okay, and we saw that to get the extrema,
Mm.
to get the
Extreme.
extrema, what
Do.
we will do, we will simply differentiate functional.
Equal
We
to
can
0.
also do
Equal to.
something like this.
Mm.
Simply what you have to do is just substitute in the functional as the place of
Mm.
u as a u plus alpha v,
Alpha V.
and differentiate with respect to alpha, and after
Mm.
differentiating just substitute
Mm.
alpha equal to 0.
Yes, sir.
Okay, then you will get the optimized alpha, or optimized u.
Mm.
Okay, and from this,
Mm.
suppose I am solving it. Okay, d by d alpha a to b, because I is this, right? F
Mm.
x u tilde dash dx, and what we will do is we will substitute finally alpha equal to 0. After doing all this we will substitute alpha equal to
Alpha equal to
0.
0.
Okay,
Mm.
so now introduce this derivative inside of this, so it will become a to b
B. D by
del f by del
del
u tilde del u tilde by
U
del
tilde by
alpha
del
plus del f by del u tilde dash del u tilde dash by del alpha, and alpha equal to 0. Finally after integrating it we will substitute alpha equal to 0.
G.
okay, and since we have to equating everything as a 0, okay. So
Yes,
what
sir.
we will do, a to b here, del f by del u, okay. Since
Yes,
you
sir.
can see that after integrating I have to substitute alpha equal to 0, okay.
Equal to
So
0.
when you substitute alpha equal to 0, this u tilde become u, okay,
Okay.
and del u tilde divided by del alpha it will become v, okay, plus this will become del f by del u dash, and this will become v dash, okay,
Okay.
and dx equal to 0.
0.
Now I have to apply integration by parts,
Parts.
okay. So what we will do, a to b, v, I will not go every step, I will just directly write v del f by del u minus d by dx
Mm.
del f by del u dash
0 equal to 0.
dx. Now there is a very important step where you will see how to get the boundary condition,
Mm.
right?
Yes, sir.
Here, when when you try to get Euler-Lagrange equation, then what you do? You do is you apply the end condition. And what is the end
Yes.
condition? When VB and VA both are
Which
0.
0.
Okay, so
Yes, sir.
in that case this term will
Will
vanish,
be will be 0.
okay.
Yes,
And
sir.
since we are taking v as a any arbitrary function, then this integrand becomes 0, then we get the
0.
Euler-Lagrange equation. This is nothing but the
Equation.
Euler-Lagrange equation,
Yes, sir.
okay. But
Mm.
is it necessary that every time the end condition will become 0? No.
No.
Sometimes, which means that we will have three kind of boundary conditions, not three, four kind of boundary conditions, okay.
Normal water.
Yeah, four kinds of boundary conditions, not only the Dirichlet. Whatever you saw earlier, that was the
Yes.
only Dirichlet boundary condition where end conditions are only 0, va equal to vb equal to 0. But sometimes this natural boundary condition also can become 0,
Okay.
okay. So here we will get what we can also get, va equal to 0, vb
VB.
equal to 0. If you write this, then also we will get Euler-Lagrange equation, okay.
Mm.
But also when va equal to 0, but sometimes del f by del u dash b can also become 0,
Mm.
then also you will get the Euler-Lagrange equation, okay.
Yes.
So similarly you will get four kind of boundary conditions.
Mm.
Are you getting?
Yes, sir.
Yeah. And fourth is del f by del u dash a equal to 0, or comma, right, comma del f by del u dash b equal to 0.
0.
So in any case, in any condition you will get Euler-Lagrange equation,
Equation.
not just only at the end points, okay.
Mm.
Yeah, let's solve one elasticity problem, okay.
Okay.
Can we take one 2-minute break? You are
Yes,
also,
sir.
I think you got tired, okay. I'm also got
Okay,
tired.
sir.
So let's take 1 or 2 minute break, then we'll come, okay.
Yes.
Okay, yeah. Are you here?
Yes, sir.
Yeah. You took rest?
Hello. What, sir?
Did you take the rest or what?
No, sir. Just refreshing.
Okay. Only you are here, right?
Yes, sir.
Oh, nice. Okay. Let's solve one elasticity problem, okay?
Okay.
The problem is an elastic bar of length L modulus of elasticity E first you try to solve, okay, then I will try to solve it. Okay,
Yes, sir.
so there is a bar here and there is a
Mm.
distributed axial load, that is function f, that is force f, which is a function of x, and there is a point load p, and there is a boundary condition, that is u at x equal to 0 is 0, okay, and we are measuring x from here,
Okay.
okay. So find find the equilibrium equation. Equilibrium equation using Euler-Lagrange equation, okay,
Okay.
and also find the associated boundary condition.
Associate boundary condition, sir.
Associated boundary condition,
What is?
because
What does it?
you will get the differential equation, right,
Yes, sir.
and that differential equation will have that is one differential equation, and you
Mm.
have already one boundary condition, but you will
Mm.
require one more boundary condition, and
Yes,
what
sir.
will be that?
Okay.
Okay,
Okay.
fine.
The force is in the axial direction of this. No?
Yes, axial direction.
We have to use the first one. The equation you have given, we only have to use that.
The trick is that to get the equilibrium equation, you have to minimize the total potential energy. And this is the
Okay.
potential energy that you have to minimize.
Okay.
Okay, so after minimizing the total potential energy, you'll get the equilibrium
So,
equation.
sir, there is a term uh, PUL. Is that constant or that depending on
Yeah,
this?
this P is actually a constant
Uh,
which has been applied at the point
uh,
here, that is
yes.
at a distance
Yes.
of x equal to L, and U is a variable.
Okay.
Okay, and here L is the total length of this bar.
Mm.
Fine.
Mm-hmm.
Yes.
Okay.
You can also use that trick, like you can introduce this thing inside the integral if you are
Yes, sir.
getting a
I have
problem,
done that.
because you can see that it is nothing but the solution of the integral
Yes, sir.
if
Yes.
p is a constant, right?
Yes, sir. I have done that, sir. Yes.
Yeah, fine. Here actually it will be in the bracket because u is a constant.
What, sir?
Here L will be
Ah.
actually in the bracket because here U is that displacement when x is L, because when you integrate it,
Okay.
it will be outside of the integral, so that should be a
Mm.
constant. So that's why it is PUL.
Okay.
Okay, because U as when distance x is L.
Okay.
Now you can
Okay.
introduce inside the integral.
Okay. Then this should be done. Okay, sir.
Hmm.
Yes, sir. I have got that.
What did you get it?
E A U dash minus P.
Okay, EAU dash.
Uh,
Okay.
minus P
Hmm. Okay,
equal to
what
minus
that is
Fi.
the final solution or what?
Final solution. What this means?
I mean, what the final solution will be the differential equation, right?
Yes, sir. This is the differential equation.
Okay. So what did you get? But that should be second order differential equation you should get.
Second order differential equation.
Yeah.
I'm not getting that, sir. Are you saying about the variational statement or the Euler Lagrange equation? Or you have to-
That you should get differential equation, right? That Euler Lagrange equation you should get the differential equation. That should be second order differential equation,
Yes, sir. I have integrated that.
right? Okay, fine. Nothing to worry. Let's solve this, okay?
Okay. Sir.
Yeah. When you take the variation of pi, then what it should be? Del pi equal to 0 to L, okay? And that will be del what I can write here? Can you tell me?
Minus p du by dx.
Here what I can write?
Uh, to
Pu, right?
only pu. If we integrate, sir, this should be du by dx, na? If we integrate that thing, then it will be u only, na?
Yes, du by del x. Yes. Right?
Yes.
Okay. Fine. So this is your f, right? This is your f. Now what I'm trying to do is I'm just taking the variation. So what you will get? Ea by 2, and that will be 2 times du by dx, okay, into d del u by del x. Fine. Minus f del u minus p d del u by dx, right?
Yes, sir.
Fine. Now I can simplify it. 2 will be cancelled out. Okay, so here will be like this only. It's correct or not?
Yes, sir.
Yeah. Now apply integration by parts here. Okay.
Hmm.
So you will get Ea du by dx du, right? 0 to L, integral 0 to L d by dx Ea du by dx del u dx. Fine.
Sir, this is the weak form, na?
Hmm?
I mean, variational statement. This is.
This is not a weak form, because to get a weak form you have to take one variation. That should
Yes,
be a
sir.
that should be a W. Yeah, you can say that this is also kind of weak form, but actually I am taking the variation.
Okay.
Okay, I am taking because it's not a kind of weak form, because
So, sir, why
again the
don't
derivative
we
will be a second order. Weak form
go
you can
with
say
the?
like when derivative fragmented, when the requirement of derivative reduces.
Yes, sir.
But here you will see that the requirement of derivative will not reduce.
Okay.
Okay.
So, sir, why don't we go the previous one with the previous one? Only we are using that del f by del y minus d by dx of del f by del y dash.
Yeah, that
That
you
is
can
equal.
also do, but the problem is here, there you will not understand from where we will get the boundary condition,
Okay.
remaining boundary condition.
Okay, sir.
There you will get the differential equation, but there
Hmm.
there will be a very difficulty to get the another boundary condition, that is a natural boundary condition.
Okay, sir.
because you will get the Dirichlet boundary condition, but Neumann boundary condition you will not get there.
Okay, sir.
Fine?
Okay, sir. Yes.
Yes. So now 0 to L f del u dx minus PL del u. Right?
Yes, sir.
And here you already know that del u equal to 0 at x equal to 0. Right?
Yes, sir.
So this will become directly 0.
Mm.
Fine?
Mm.
So now what it will be? 0 to L, I can write del d by dx EA du by dx minus f del u dx
Mm.
plus del u. Okay, sorry, yeah, here actually not completely. Actually, you have, first we have to apply 0 to L boundary condition. Okay, when at x equal to 0, then we will write del u equal to 0. But still, at x equal to L will remain. Okay.
Okay.
So
Okay.
del u L, here you can see EA du by dx
Minus P.
minus P, and then
L should be there.
x equal to L equal to 0.
Okay.
Right?
Yes, sir.
Here you can see that earlier one, which was when x equal to 0, that get lost.
Mm.
Okay, but when that remaining, when delta u at x equal to L, that will remain.
Okay.
Okay, so here you can
Yes, sir.
see, here you can see for any arbitrary del u, for any arbitrary del u,
Arbitrary del u.
this part
Yes.
should be 0. This
Yes,
part
sir.
should be 0.
Zero.
So that will be del d by dx EA du by dx minus f should be equal to 0.
0.
Okay, and when this
Yes, sir.
becomes 0, which means that for any arbitrary u, because we have not set del u at x equal to L, so which means there is no such guarantee that del u at x equal to L will become 0, which means that this part should be 0.
This 0.
Okay,
Yes.
so which means that EA du by dx minus P at
Equal to
x equal to
X
L
equal to
should be 0. So
0.
this is what? Natural boundary condition.
Mm.
Fine?
Yes, sir.
So which means that we got the differential equation, and this differential equation is nothing but strong form.
Yes, sir.
Strong form. This differential equation is nothing but the strong form.
Strong.
And it is also a equilibrium equation.
Mm. Yes, sir.
How do you know that? Do you know already? You would know that this is the you know that?
No, sir.
Okay. This is the equilibrium equation
Okay.
for any kind of problem.
What are the parameters in this? Variables in this?
Here ij, here you can see that if comma is representing, which means that there is a contraction. There is a contraction. Here B is a kind of body force. Bi is a body force.
Okay.
Okay, and sigma is a Cauchy stress.
Okay.
Cauchy stress.
Stress.
Okay, so when you write in the form of differential equation, then I can write del sigma. Here I will go from 1 to 3, and j will also go from 1 to 3.
2,
Okay, so which means that if you can see that only the free variable is I, but j is a dummy variable. When some index repeats, then it becomes a dummy variable. Okay,
Hmm.
when some index repeats, then that index
Hmm.
will be dummy variable.
Okay.
Okay,
Yes.
and when the index is not repeating, which means that that index will be what, free variable. Okay, so here
Yes.
I is free variable. Okay, and j is
Yes.
dummy variable.
Dummy variable.
So which means that here you can see that j is repeating here, which means that
Hmm.
on the same line you have to apply j equal to 1 to 3.
3.
But on the same row you will write I equal to 1, but when you
Hmm.
want to vary I equal to 1 to 3, then you have to create two more row. Okay, which means that
Okay. Yeah.
here I equal to 1, I equal to
2.
2, I equal to
I equal
3.
to 3.
Okay, but here what, j equal to 1,
1.
j equal to
J
2,
equal
and j equal to 3. So
to 3.
what it will become, del sigma by del what,
Del.
tell me. So here I can write, I am writing I equal to 1 1, so I will write del sigma 1 1 del
1 by
x what,
x.
tell me.
1.
Hmm?
1. 1.
Only one, think about it.
Yes, sir. 1 1. Not getting, sir.
Hmm? Not really. Okay, so what it will be, sigma 1 2 sigma what, j is repeating here 1 2, so that will be x2
X2
plus del sigma 1 3 del
by
x3
x3.
plus rho b 1 equal to
Hmm.
0.
0. Hmm.
Okay,
Okay.
similarly what will be the another equation, sigma 2
1
1.
2. 2
Here
1,
now
sorry.
I
Huh.
has changed,
Yes, sir.
so
Yes,
that
yes.
will be sigma 1
Del x.
del
Hmm.
sigma 2 2 del x2 plus del sigma 2 3 del x3 plus rho b2 equal to 0. And what will,
X1, X2, X3, what are they? These are the coordinates
yes,
in
these are variable
axis.
in coordinate system,
Okay. Okay, sir.
variable in coordinate system.
And the sigma 1 1 are these the stresses?
Cauchy stress in different depend, this is the
Okay.
state of stress.
Yes, yes, I get it.
Fine.
Yes, sir, I get it.
Yeah, so that will be state of stress. Now sigma 3 1, sigma x1, sigma 3 2,
3 2
sigma
sigma x
x2,
x2
sigma 3 3, sigma
by
x3
x3
plus rho b 3 equal to
3 equal to
0.
0.
Okay, now
Yes.
I told you, when you simplify all these for this problem, for this
Okay.
problem you will get this differential equation. Okay, how? Because this problem, this elasticity problem is nothing but the plane stress problem.
Okay.
Okay, so which means that here not the plane stress only, it is also a uniaxial problem. So here when you take an element here, then you will
Hmm.
see that here
No.
sigma xx,
Sigma.
sigma xx, okay, and there is no sigma xy,
Yes, sir.
there is no sigma yx. You already know that sigma xy and sigma yx are both same, okay, from
Hmm.
the momentum
Yes, sir.
equilibrium, okay, from angular momentum
Yes, sir.
equilibrium. Okay, sigma zz also equal to 0, sigma zx also equal to 0, sigma
Jesus.
z is also equal to 0. Okay, so only will remain is this.
Sigma x.
Okay,
XX.
so now substitute everything here. So what you will get, del sigma 1 1
One.
sigma
Hmm.
xx divided by x plus this one is also 0, this one 0, this one 0,
Zero.
and
Zero.
there is a force,
Hmm.
there is a force. So
Force.
what will I write is, in this case this B1 is nothing but the F1.
Okay.
Okay, there will be a F1 equal to 0.
Zero.
Again, what will be the sigma xx? Okay, so here
Hmm.
from the constitutive equation of the linear elasticity, we
Yes.
already know that sigma
Yeah.
xx is EA
A.
del u by
Do you bet
del
del X?
x. Okay,
Yes.
okay, now substitute this, so you'll get d by del x EA del u by, actually this is a strain. This
Hmm.
is
Yes, sir.
what? This is
That's
strain.
true.
And from the
Hmm.
definition of strain, since it is a uniaxial, so that's why
Hmm.
only this part will survive, because here yy is also xx. So
Yes.
when it become 2 times, then 2 will cancel out, then it will become del u by del x. So it will become x plus, and here rho will be absorbed. Sometimes in some books it is only write b1 b2 b3, sometimes they write rho. It depends on
Hmm.
you are taking per unit volume or per unit mass.
Okay.
Okay, so in this case what they are writing, on this basis we can directly write f1,
F1.
or direct write f only. In this case it is f.
Hmm.
Fine.
Hmm. Yes, sir.
And since it is single variable, then I can directly write, at the place of d I can write this. Can you see that this is nothing but a strong form?
Yes.
Okay, the
Yes.
same thing,
Yes.
whatever you got it. So
Hmm.
there is a conclusion that if you
Hmm.
want to get a equilibrium equation,
Hmm.
then you can directly get it by minimizing the total potential energy of the system.
Yes.
Fine.
Okay.
Yeah. So we can apply the variational calculus in very complicated problems, where
Hmm.
you can easily get the equilibrium equation. Okay, so this is a one kind of elasticity problem, we got it. Okay,
Yes, sir.
do you have any problem here?
Mm, no, sir. Sir, actually, my problem, what I have solved thing,
Hmm.
uh, in that I have not taken the delta U thing.
Okay.
I have, you had said that if you go with the EL equation,
Hmm.
we will get the equilibrium equation. But I'm
Okay.
not getting exactly what you are getting here.
Okay. 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 So which me okay, yeah. The problem is you directly use the that Euler Lagrange equation, right?
Yes, sir.
Hmm. And the Euler Lagrange equation, I think you might have lost one derivative.
No, sir, I have not lost any derivative. Actually, how can I say? The thing you have insert into the integral thing minus
Hmm.
p du by dx.
Okay.
Should we consider that for the EL equation, or should we neglect that as
Okay.
this will
Let's
be
do this. Let's do this
okay?
by Euler Lagrange method.
Okay, sir.
Okay. So what is the f here?
F is EA by 2
EA by 2 du by dx
square bracket close minus FU
minus fu
FU
minus p du by dx.
du by dx.
Right? So
Yes,
what
sir.
we will do is del f
Del
by del
del U
u minus
minus
d by
d by
dx
del
del
f
f
by
by del
dx.
u dash.
Hmm.
Okay, equal to
Yes,
0.
0.
Or you can also write here f as ea by
U
2 u
U
dash
dash
square
square
minus fu
U
minus
P
p
U.
u dash. Right?
Yes. Yes, sir.
So what is the del f by del u? simply f minus f,
E. Yes, sir.
simply minus f minus
Minus
d by
D.
dx, and del f by del u dash. Del f by del u dash means you have to
EF
find
by
the derivative. So 1 by 2 ea
EA. 2
2
U dash.
times u dash, okay,
Minus
minus p equal to
0.
0. So what's the problem here? You are already getting, no?
Sir, there is a minus P thing now.
But
Extra.
p is a constant, it is not a variable with respect to x.
Okay, okay. Okay, so if we
Hmm.
differentiate that thing, yes,
It
sir.
will become 0, right?
Yes, sir.
So directly
Yes,
you
sir.
will write d by dx
DX square.
ea, and at the place of u dash what you will write? Del u by
D by
del
del
x,
X.
or you can also write du by dx, since
Du.
it is a single variable, so it will become du by dx. Okay.
Actually, I have integrated this thing, so I am getting the.
It's fine. That's why that expression came outside of the integral, because it was a constant.
Yes, sir.
Okay.
Yes,
This
sir.
part, why it came outside of the integral? Otherwise
Um,
this part also should came outside of the integral, but it cannot. This f
okay.
cannot go outside of the integral, because f is a function of x,
Yes, sir.
but p is independent of x.
Yes, sir.
That's why
Remember.
this integral, when you try to to integrate this, then p is a constant, then it will go outside of the integral, then it is coming outside here. Okay,
Okay.
fine.
Yes, sir.
Any problem?
No, sir. That the thing.
Okay, so in the next class we will try to solve every assignment problem.
Okay, sir. The problem which I have tell tell earlier, that will be the. Can you?
Okay, what is the deadline?
Deadline is 8.
8th August. Okay, first I will try to stop the video recording, then I will try to talk casual thing. Okay,
Yes, sir.
yeah, okay.